All right, this time we're going to talk about one of the more important bridge theorems we have that connects work to other things, something called the work energy theorem. So consider a single force F acting on a massive object of mass m is moved through a distance d, i.e. our standard thing. Further assume that d is the only force acting and it acts in the same direction as d. So we're going back to our original setup for what work is. But in this case, since it's the only force, then the total work that's done is the work done by F, because duh, there's nothing else. So the total work is F times d. But since F is acting alone, it's also the net force, and so it creates an acceleration that takes the object from speed vi to vf during that motion. From 1D kinematics, we might remember that vf squared is vi squared plus 2ad, in constant acceleration cases at least, and that from the Newton's second law, of course, the acceleration is F over m. Putting those together, we say vf squared is vi squared plus 2 times a times d, but a is F over m. And then we do some simplification. Cross multiply by a half m, and we get something like a half mvf squared is a half mv squared plus fd, and we can rearrange instead by saying that fd is a half mv squared minus a half mvi squared, or it's the change in the quantity half mv squared. Of course, fd is total work, so now we define, and I want to stress this, we define the kinetic energy by saying the kinetic energy of something is 1/2 its mass times velocity squared. So now we say there is some state property, something that depends only on the mass and the current velocity, which is called kinetic energy, and what we have come up with is that the total work done on the object is the change in kinetic energy, and that will continue to be true throughout the whole rest of physics forever and ever. Kinetic energy, as we know, is associated with the motion of things because of the v. All right, straightforward and a quick one. In the figures below, balls are traveling in different directions. The balls have the same size and shape, but have different masses and traveling at different velocities. Draw a blue circle around the case or cases with the highest kinetic energy, and a red circle around the case or cases with the lowest. Again, pause the video and then come back and we'll solve it. The easiest thing here would probably be just to actually find the kinetic energies. So here we have 1/2 times 2m times v squared, which is just mv squared. And here we have 1/2, let's do a different color, 1/2 times 2m times 2v, but then squared. So this is a half times 2 times 4, so 4mv squared. And then here we have 1/2 times 4m times v squared, which is 2mv squared. And then finally, we have a half times m times 2v quantity squared, which is also 2mv squared. So our largest is b, and our least is a. And we can in fact say that a is less than, and we find that c is the same as d, which is less than b. A couple important things. I've cheated on a couple different levels. Firstly, we put a lot of restrictions on f to make it work. That makes the result algebraic. We can let f and d vary. In other words, it doesn't have to be constant acceleration. But then you need to use calculus to prove the results, and the result is the same, so we don't get anywhere for it. But introducing the complication of varying f or d introduces the complication of needing calculus, which is one reason why calculus is at the root of the dawn of physics, that the invention of calculus was a prerequisite and motivated by physics things. Much more seriously, I haven't actually defined what energy is, and I'm not gonna. It's a very difficult concept to make precise, and most textbooks will fall back on something like saying energy is the ability to do work, but then later on they'll define work as the transfer of energy, and those things are circular. They don't really come out somewhere. So mostly energy is a property things have. It allows them to do work. I guess that helps, but it allows them to exert forces across distances. That's sort of the best you can do. Ultimately, we use energy as a concept because it's useful and it's easy to calculate. It's not too far off to think of energy as capacity to exert a force across some distance. All energies basically come back to that in some level, although we'll see it's mostly kinetic energies that do that specifically. And then an analogy which I think is helpful is to think of energy as the currency of the universe. It's the money the universe spends to get things done. And just like you can move back and forth across accounts, and have different forms of it, but you need to actually move the energy the money to get anything done. Likewise, energy comes in many different forms, but you need to do work to move it from one form to the other so that you can do stuff with it. You can change the state of your system. It's actually not a coincidence that our modern concepts of economy arose at the same time and really from the same people as the concepts of dynamics, and that's why you talk about things like the velocity of money in economics. All right, so if it's useful, how do we use it? Well, work-energy theorem will tell us something nice. If we compute the energy at the start and end of a process, in this case kinetic energy, then we can say something about the forces that must have acted. That if the total work is positive, the object must have gained speed. If total work is 0, the object's at the same speed at the end. And if the work is negative, the object lost speed. Now we need to be careful because energies are state functions at this moment and some other moment. Doesn't tell you what happens in between. So if your total work is 0, that doesn't mean that it only stayed at constant speed, all right? It's not constant speed, just that the speed at the moment you started and the moment you ended happened to be the same. Also, it's probably good to draw here that energy itself is also a scalar. So it doesn't matter what direction you're headed. Kinetic energy doesn't care, and actually none of the energies will care where you're headed. They're always scalars. And so also having the same speed doesn't necessarily mean you're moving in the same direction. So you could have something which has turned around, for instance, and come back to the same speed. When forces are constant, then energy is redundant. You could always just apply Newton's law and the constant acceleration equations. But energy turns out to be very powerful because in many situations it's impractical or even impossible to track all the forces, but the energy might be easy to follow or to compute. And we'll see some of those cases as time goes on. And then in future work, in things like thermodynamics, it becomes really impractical to do all of the forces. But you don't have to. You can track energies instead. All right, situation shown below has before and after snapshots of a car's velocity. All the cars have the same mass. Draw a blue circle around the cases with the most work done, and a red circle around the cases with the least work done. Take a couple of seconds and then come back. Key thing here is we're not given any forces, so we can't do F times D. We're also not given any distances, but we are given velocities and masses, so we can talk about kinetic energies. So pretending the mass is 1, then we can say that the kinetic energy before on this thing is, let's make the mass 2 actually, so half times 2 times 10 squared, or 100 units, and this is 40 units. What I'm saying here is the kinetic energy is 1/2 times mass times v squared, and if I've chosen the mass to be 2 units, whatever it is, then I can just talk about v squared, right? We have just v squared as proportional to v squared. In case B, we start with 100, but we end with nothing. In case C, we start with 100 and we end with 100. And in case D, we start with 400 and we end with 400. So now let's talk about our delta. 40 minus 100 is minus 60. 0 minus 100 is minus 100. 100 minus 100 is 0. And 400 minus 400 is 0. So we can see that since the work total is delta K, we can just say the biggest delta K so that's interesting. The most work done is here. We do 100 joules of negative work. And then the least are these two. Oh, except that way back when I was wrong. Forgot to write a 0 here. 20 squared is 400. So let's clear out those things. That means, scribble, scribble, scribble. This is really 300. That makes life a lot easier, actually. And so we can see the most work done is A. The least work becomes interesting because minus 100 is less than 0. So that's the least work. We might find that obnoxious, but that's the way math works. If you want in terms of magnitude, of course, it would have been C and D rather than B. This sort of problem is what we call a bar energy chart, and we'll be doing a lot of these, I think, as time goes on. 2 kilogram object changes the velocity as a force acts on it for 5 seconds. It changes velocity from 4 meters per second east to 6 meters per second east. Show the work and energy bar chart for this process. Bar height should be in correct proportion to one another. It means we can't tell what the scale is, but we can at least make sure they have the right scale. So since the kinetic energy is 1/2 mv squared, we can make, and the m's are the same, v squared is what matters. So we start with 16 units and we end with 36 units. It looks like if we make each block 4, we're in good shape. So let's say that our kinetic energy starts off with, at the start we have 4, actually, yeah, well, that's fine, which is 16 total units. And at the end we have 36, which are 9, so 4, 8, 9. That's actually just exactly what we have here. So the work done has to be whatever gets us there, which must be 20 or 5 blocks. And that's because we know that these two have to add up to that one. So that's how we end up doing that. Notice it was hard to compute that ahead of time. We had to say, oh, the work was the difference. All right, so let's practice this one now. Velocity of tugboat increases from 2 meters per second to 4 meters per second in the same direction as the force is applied through the tugboat for 20 seconds. Fill in the missing bars for the work and kinetic energy in this process. All right, well, we know that we had from 2, which is going to be 4 units of energy, right? 1/2 mv squared is 4 units of energy, and we end up with 16 units of energy. But they tell us that 4 units of energy, oops, don't know what happened there, that 4 units of energy is 2 blocks. So each block must be 2 units of energy, whatever they are. So we know that this is 4. And we want to end up at 16, which is 4 times as large, so we have to end up with 8. 1, 2, 3, 4 times as large. And therefore, the work done, I've been trying to do colors differently, so let's just do this in red. Sorry. I'm just trying to do colors consistently. Actually, in fact, let's just clean up. That we had 4 units, now we go to 16, which is 2, 4, 6, 8 blocks. So something like that. And to get there, we must have done 12, which is 1, 2, 3 sets of 2. Because again, the initial plus the amount of changes has to equal the final. All right, and then the velocity of tugboat changes from 2 meters per second to 4 meters per second in the other direction as the force is applied to the tugboat for 20 seconds. Fill in the missing bars. Notice the setup is the same. Also, just keep in mind that we still have 4 units becoming 60 units of energy. In other words, it doesn't matter that the direction, right? Direction doesn't matter. And so this is going to look just like the one above. And we get something that was identical. Didn't matter that it turned around. That must mean there must have been some work slowing it down and some of the work speeding up again on the other direction, but none of that matters. The network is the network. Compute the work needed to stop a 50 kilogram person who's traveling 25 meters per second, which is highway speed. And then if the stopping distance is 0.03 meters, what force would we have to apply? And if the stopping distance had been 0.3 meters, what force would have to be applied? So the first bit is relatively straightforward. The total work done is the change in kinetic energy. So we end at 0 and we start at 1/2 times 50 kilograms times 25 meters per second quantity squared. This is negative because we're slowing down, 15,625 joules, which should probably really be minus 15 kilojoules because we certainly have enough sig figs for 4 digits there. And then we'll say, well, the work total is also the force times the distance. So we get the force, this implies the force is the work total over the distance, or minus 15 kilojoules over 0.030 meters, which is something like 500,000 newtons. That's a pretty strong newtons. Of course, we're stopping in 3 centimeters, so that's maybe not too surprising. What if we had increased the distance by a factor of 10? Well, we can see that if we increase this distance by 10, then we must decrease the force by 10. So without any calculation, it must become 50,000. That's more or less what an airbag does for you. It reduces you from pulp to just hurt, from a small distance to a huge force to a somewhat smaller force. Looking back over it, I actually rounded badly. Of course, this should have been minus 16 kilojoules. And that makes these 520,000. And therefore 52,000. No change really, except that the rounding was bad.